Today's video will explain how to use the different types of arrays in C++. Hello, I'm James Helfrich. There are four types of arrays we commonly use in C++. There is a built-in static array, a built-in dynamic array. There is the standard template library array type, and the standard template library vector. This video will explain each, demonstrate how to use them, and share some best practices about when to use each type of array. There are four types of arrays in C++. The first is the built-in static array, and this is probably the array type you first used. We specify the base type, in this case an int, the variable name, in this case a, and the number of elements, 10. Notice this must be a constant or static value. It cannot be a variable. Next, we have the built-in dynamic array. Here we specify the data type, integer pointer, the variable name, a, and then we have to say new to allocate the number of elements. In this case, I'm going to allocate exactly 10, but here I can specify the number of elements that is known at runtime, not at compile time. Don't forget to delete it when you're finished. Now we have the standard template library array type. The data type is std::array, and we have two template variables. The first, the data type, int, and the second, the number of elements, in this case 10, and that 10 must be known at compile time. Our variable name, of course, is a. And the final is the standard template library vector type. The data type is std::vector, and we must specify the base type, which in this case is integer, the variable name a, and here I'm going to specify ahead of time how many elements there's going to be, 10, but we can adjust the number of elements dynamically by using pushback or popback at runtime. First, let's take a look at the built-in array type. A couple things we'll notice about it. First of all, we must specify the data type. In this case, it's a float. And second, we must specify as a constant or as a literal the number of elements in the array. Now, some compilers like G++ may let it slide and let you specify a variable here, but that's a strict no-no. It's against the C++ standard. Most compilers will give you a warning if you try to do that. And the way G++ does this is it allocates a whole bunch of space on the stack, which may or may not be sufficient. If they allocate too much space, then you're going to have wasted space on the stack. If they allocate not enough, you're going to have a buffer overrun. So it's just bad news. Don't put a variable there. Now, the cool thing about the built-in array type is when this variable falls out of scope right here, then that memory will automatically be freed. I don't have to worry about that. Okay, the next type is dynamically allocated. First of all, I declare the pointer, and I'll call it dynamically allocated. Then I use new, the base type float, and I can specify the number of elements as a variable in this case. Now, the trick about this is I must remember to free it, and that's problematic because if I forget to free it, I have a memory leak. And so this is why we try really hard not to use dynamically allocated unless if it's in the same function, so it's easy for me to verify that I've newed and deleted it, or if it's in the same class, in which case I usually put my delete in the destructor. But if you rely upon another function to delete it for you, that's a recipe for disaster. So it's a best practice to not do that. The next one is a standard template library array type. The full name is std::array, but since I said using namespace std, I can simply say array. And this has two template variables. The first is the base type, which is a float, and the second is the number of elements. Now, this number of elements must be known at compile time because it's a template, and templates are expanded at compile time, not at runtime. Now, this memory will get freed automatically when I fall out of scope, so I don't need to worry about delete. Now, of course, the built-in array, the syntax is way easier than this chevron, data type, number of elements notation. However, the cool thing about the standard template library array is it has a .size method. So I don't need to pass the size of the array as a second parameter. The final type of array is the standard template library vector. Just like with the array, I need to specify the vector library, otherwise I will not be able to use it. The full name is std::vector, but since I use namespace std, I can get rid of that and just say vector. And I must specify the data type in float. And so we kind of have this kludgy interface similar to array, but I have to specify less parameters. Now I can add and remove elements on the fly with vector really easily, when I can't with the other types. The real difference between the built-in data type and dynamically allocated versus the standard template library is when I pass it to a function. Okay, so now I'm going to write a function. I'll call it my function. I'm going to pass in a built-in, a dynamically allocated, a standard template library array, and a standard template library vector. So up here, I have my four parameters: my built-in, my dynamically allocated, my array, and my vector. Now notice that built-in and dynamically allocated are pointers, so I don't need to pass it by reference. I automatically can read and write it. But my array and my vector must be passed by reference here. Now, if you want to make them read only, then I'll have to make it const, but right now I'm not going to make it read only. Now, if I say size of built-in, it's not going to tell me how many elements there are in this array, but rather it's going to tell me the size of a pointer. And so I have no information indicating how much memory is associated with this particular array. But dynamically allocated, it will tell me the size of the pointer, but not tell me the size of the array. So in order for me to understand how many elements are passed, I need to pass another parameter. Okay, so now I pass in another parameter, which tells me the size of built-in, another parameter that pass size and dynamically allocated, and because the size of does not work the way I expect. Of course, I want to find the size of the array. All I have to do is say std array dot size. And if I want to know the number of elements in my vector, all I have to do is say std vector. So it's a huge advantage when passing as a parameter to use the array or vector type because I don't have to specify the separate parameter, which I'm likely to mess up and get incorrect. Now, which of these four array types do you use at a given moment in time? Use a built-in static array when the size is known at compile time and when the array is not passed as a parameter to a function or a method. Now, of course, we can pass an array as a parameter, but we must also remember to pass a second parameter, which is the size of the array, so the client knows how many elements are going to be in the array. We use a built-in dynamic array when the size is not known at compile time, because it takes more computational effort for the computer to allocate the block at runtime. This is useful when the array remains within a single function or class, because we must remember to delete it. And if it's not in a single function, or if it's not in a class, then it's likely the person we pass the array to will forget to delete it. So I usually put my array allocation in the constructor, and I usually put the freeing of the array in the destructor when it's in a class. With the standard template library array, the size is known at compile time, just like a built-in static array. And here, if I'm going to pass that array as a parameter, I always use the array type. Why? Because I have the .size method, so I don't have to pass the size as a second parameter. This makes it far less likely I'm going to make a mistake and have an error. And I use a standard template library vector every single time I know that the size of the array is going to change dynamically. Otherwise, I have to keep track of all this and re-implement the functionality of pushback, resize, insert, or pop back. And rather than implement that myself, I'm going to rely upon the standard template library. You can learn more about the vector in the C++ data structures textbook.